All right. Let's hide that thing. So yeah, I was essentially asked if I could talk about something again, and well, there is something that we worked on a bit. Some friends of mine and I, because we're hacking on a bunch of gadgets, essentially, like let's say like small TV boxes and devices along those lines, and each and every one of them is using something that you may also know, the device tree. And well, let me briefly show you the agenda for today. I will talk a bit about the history because it actually has a behind the device tree visualizer, and then I will get a bit into the technical parts. And with that, first, I want to thank you a bit to my hackerspace because Chaospot in Essen, well, I'm currently in another hackerspace, but coincidence. Um, there were actually a bunch of people who helped me keep things going or get things going at some point. Um, so yeah, uh, kudos to them. So yeah, let's talk a bit about history. And device tree actually started in the early 90s already. It was even a standard in IEEE 1275. That was the open firmware standard. That's where the device tree was initially being described. What it does is essentially, it's a description language for hardware topology. So when you look at a typical SoC, like a system on a chip today, you have your all the peripherals, all the different processing cores, and so on. And device tree is for describing all of that stuff so that an operating system can know about the hardware it's actually being run on, right? So yeah, otherwise there are many devices which cannot just be discovered at runtime. Um, it's now being used, well, famously in Linux, then also in U-boot, in Zephyr, OLPC, the one laptop per child project was also using it. FreeBSD also uses it for some platforms, and there's a bunch of other projects actually, including Apple, even back in the days, was also using it. And I think they might be using a very lightweight version again today. Um, anyway, and all those projects are actually using it a bit in different forms. For example, Linux is using the device tree at runtime commonly, not necessarily, but commonly. So, when the kernel starts, the first thing it does is it will look at the device tree and then, see where it's at. U-boot is a bit similar. Uh, except for some parts. And Zephyr doesn't use the device tree at runtime at all. It actually just generates its code for it via device trees. Anyway, not going too much into details here. Uh, from my point of view, the device tree language is not too elegant. It's like, for example, in the Linux kernel, it's being attached via bindings, and the bindings always need to fit. So you cannot just take a random device tree and then take a kernel, and they won't just fit together. They will actually have to match up. So that is why the current device trees are commonly developed within the within the Linux project, and then they are, if you look at the U-boot mailing list, they're commonly synchronized over to U-boot so that they are sort of similar. They still have a bit of a different view, those two, but essentially they're very, very similar. Um, there is only a few fields that are actually specified. So there is a device tree specification that you find at devicetree.org. It's currently version 0.4, so not even a 1.0 version yet, even though it's already 30 years old or something. But yeah, it's like mostly, as the things are, that's how the device tree is used today. So yeah, if you look at the like Linux kernel, for example, at large, you will find that the trees are a bit different between like different chips and so on. Well, and the device tree size can also differ significantly. It can be just a few hundred nodes, or even just a handful, or it can even be like 1,000 nodes, for example. A typical SoC, which supports, let's say, HDMI and lots of Ethernet and a bunch of USB ports and all of that glory, that will actually reach 1,000 nodes very easily. Like a current Apple laptop, for example, that Linux has been ported to those. So yeah, that's where you will find that. And the tree is actually a lie because in reality, the hardware actually does have some cycles, if you will. So you cannot perfectly map everything. You may know, for example, for clocks, there is actually the clock tree itself, and that goes to lots of peripherals, right? So yeah, if you wanted to draw lines in the device tree that also includes how the clocks are related, you would suddenly get circles. but yeah, it's sufficient enough for what we're using it for nowadays. Some previous work at the Linux Plumbers Conference, for example, also ELPC, hang on, ELCE, the European Linux, the Embedded Linux Conference Europe, right? Those places is where people talked a bit about device trees and, tried to develop some tools and so on. Some have never seen daylight, so those are stalled projects. Some, actually made it. So yeah, gradually people introduce more and more tools into the Linux kernel. There were other tools like the component inspector by Freescale, which is now acquired by NXP. That was a proprietary Eclipse plugin. There was another suite that it was part of that is Unobtainium now. Somebody made something called FDT Viewer that was written in C++ with some Qt for the user interface. I think that project hasn't seen much maintenance in more than a year now. Another thing somebody made, it's called DTV Demo. Well, you already see the name, right? I think it also hasn't seen too many commits recently. That was only for device tree sources, if I remember correctly. We will talk about that in a bit as well. And then there is a Visual Studio Code plugin that somebody created, so you get some syntax highlighting for the device tree source language. And well, the device tree visualizer tool that I made, I call it DTViz. It's also running on a web platform, so technically we, could find some synergies and maybe also support VS Code with what we just made. So yeah. Now let me briefly talk a bit about DTViz, and DTViz is actually part of a larger project that I started at some point, which is called Platform System Interface. It's really just a collection of some design ideas and stuff and a bunch of tools so far. Yeah, not really well worked out thus far, but yeah, feel free to look at GitHub, and that's also where you find DTViz under that project. Yeah, I also talked about that a while ago. If you look at those slides again later, I will share the link and so on. You can also follow the link to this PDF here, which is very broad in a larger direction. So what is the device tree visualizer? Well, it's a tool that will take a device tree blob. So that would be the binary representation of a device tree. And then it will parse it and visualize it, well, in the tree form, as you know how you would draw a tree, right? Like, you maybe did that at school or at university, maybe when you learn about data structures and, trees. We just draw the nodes and then we draw the edges, and that's how we visualize a tree. So yeah, it's really just a device tree visualizer, as plain as can be. What you see here is just one example. So you see the root node, right? And then you see the lines going down to some other nodes and they expand again and so on. This here being a very, very simple example. There are others, as I said earlier, which can be like 1,000 nodes or even more. So now there are a few challenges with that, and I want to briefly talk about them, not go too much into detail because, we keep it short here. So one question is, how do we actually distribute those nodes, right? So they must not overlap, at least it would be good for a start so that you actually get a bit of an overview. So they need to be nicely distributed. Then the question is, how do we make good use of space, whatever good means in a specific sense? People might have different ideas what a good distribution of nodes is, and that strongly relates to actually the the shape of a very specific tree. And by shape, I just mean like the depth of the tree and the width maybe, or where you can find like clusters of nodes and stuff like that. Well, and then a node itself in a device tree can actually have like one or two up to like some dozens of properties even. So do we want to show all those properties? Probably not to have an overview, right? So yeah, we can apply some graphical interface ideas to actually show that in a maybe a pop-up or whatever. So yeah, here are some examples of my first draft. That is before I started writing a node distribution algorithm that actually makes sense. So on the left-hand side, you see something that is very loosely distributed. That was where I arranged nodes a bit by hand. And on the right-hand side, you see something where I use an algorithm that is apparently not a very good idea because you see there are things overlapping and you don't even know what belongs where, right? So if you look on the left-hand side, you see there are lots of lines which are very close to each other. That is because it was a very large tree. And then here is an excerpt where it goes to the right. And well, it's really hard to see where, for example, this here belongs. So here it says port, and then here it says endpoint. And now there is also a line going here from there, right? So that was apparently not the best algorithm. So yeah, there are some strategies. One is an even distribution, and I will show a demo in a bit where we can see that again. Another idea is to collapse the tree, or at least parts of the tree. So if we wanted, we could just show the root of the tree for a start, or maybe the first layer below the root, and then gradually expand things when you click on them. Or we just show everything, and if you want to hide a subtree, you just click on the specific node, and we can do things like that. More or less easily. That means we need to do some state management at runtime, but it's okay. It's doable. It's like no magic behind that. People have done that many times before. So this here is a visualization of the algorithm that we're using. And I will briefly describe what you're seeing here. So we are looking at a very small tree, to keep the example short. And this tree has a root node here. And you see every node actually has a number in it. And I will come back to that number in a bit. Well, first you can see this is not like the tree isn't balanced, right? So it's a bit different between left and right. So on the left-hand side, we have a lot more nodes than on the right. Here we just have 3 down there. So now the question is, how do we want to distribute those? If you wanted to just manually place all of the nodes, I mean, that is always possible, right? It's just too tedious for, let's say, 1,000 nodes, but for this example, it would be okay. Now you can think about, okay, how do I do that? And one very trivial solution is you start at the lowest layer, like at the leaves here. That would be right here below this line. And now you start, just putting one node next to each other. And then you draw all the lines to its parent node, or their parent node, right? And what you do here is you just give them the very, very same space between. So yeah, now they have a well-defined placement. And now you can see, okay, they're like exactly this wide, just like the line below it. So where do you place the parent node? Well, right in the middle above that, right? Now you can continue with this. Now we can draw a box around this here, and we can use that as the width of a new artificial node, or virtual node, if you will. And that would be just as wide as 3 nodes. And that is exactly the number that you see here. So you might know the term weight. So for many applications, we use weights in trees to describe well, how much a part of a tree or a node in a tree weighs. And in this scenario, we're using the maximum width of all the underlying nodes here. So in this case, we have 3 children here. So on that lowest layer, so we collect them as 3. And well, now we go to the next layer. So we look at the sibling of this node here. Well, these siblings here are nodes as well. So there is one more and one more. So they would now add up to 5. So where would you place the next node? Well, right in the middle here of this whole thing that we see here, right? So yeah, and that is exactly the algorithm that we implemented. It took a bit of back and forth to get it right in the implementation, but we succeeded eventually. Well, so effectively now we do not have any overlaps of at all, but it might be that a tree grows very, very wide, and that is actually because the SoC platforms that we have today are designed exactly like that, right? So when you go from the core of the SoC to some peripheral, the path is not too long. It's maybe 7 levels deep, and that would already be very, very deep. But there are many, many peripherals and other properties that are necessary to express in a device tree, and that makes it very, very wide. Yeah, and with that, let's look at a small demo. And I've prepared something that is small enough to have a look at. And you can also try this out yourself on GitHub. So on GitHub, if you look at the Platform System Interface project, DTVis is right under it. And there is a link here to a deployed version of this. So this tool is running fully in your web browser. There is a button up here which says load DTB. So I'm clicking that button now, and I'm loading a device tree blob from my file system. And for a start, I'm using this here. This is coming from Zephyr. Well, I just used the device tree compiler to take the device tree source from this Zephyr part here, and I transformed into a blob. So yeah, this is now the binary representation, and it's very small. So I just selected that, and you can see the result here now. It's actually not that much. And let me just go to full screen so that we can see the whole thing. So you see it's not too wide. And you see this distribution that I just described, right? So we have the root node here at the top, and it's exactly in the middle. And then everything below it is nicely distributed. And you can already imagine what happens here. Well, if you have a much, much larger tree that mostly goes in width, so you would end up with very, very long lines in both directions. Yeah, that is, as I said, a current challenge. So we will see if we implement some collapsing feature, like, you could click on this here and then you would hide everything underneath here. This would shrink to, a weight of 1, and then everything else would, fit together a bit nicer. I will just load another device tree so that we can have like, another example. Let's use this one here. This one is a bit larger. As you can already see, it goes very, very, very wide. And well, this is, if you look at the Linux source code, what you would have in a textual form, and instead of going in width, you would have a file that is very, very many hundreds and thousands of lines long. Now, if you zoom in here, you can actually zoom in. You see the actual details. But yeah, right at this point, this is not too useful yet, right? So yeah, that's why we're working on things like collapsing and so on. So yeah, anyway, this is, of course, since it's an open source project, everyone feel welcome to, file your issues if you have any ideas or something, or contribute directly. And with that, I will head over to some implementation details that we're dealing with here so that you roughly know the setup. So this here is in part written in Rust, and the actual parser itself, the full library for it, is actually written in Rust. And to make that run in the browser, we're transforming it to something that is called WebAssembly. So in a modern web browser, what we have is actually two runtimes. One is for JavaScript, and the other one is for WebAssembly, which is essentially a bytecode machine, if you will. It's rather simple. So that was actually also part of the design idea. It doesn't only run in web browsers, you will also find it in other places. AWS, for example, also offers WebAssembly runtimes for, your compute loads if you want. So now, well, how did this happen? So the question was like, what if, we could write our code in Rust, right? So we compile that, and well, we compile it to WebAssembly, and out of a sudden we can use it in an app. Like, how does that work? Well, it's sort of, it feels a bit like magic, because we can now actually use native code on the web platform, right? So usually if you write something in, like, I don't know, Rust or Go or something, you would be used to run that outside the web browser, right? So like directly in your operating system. But yeah, as I said, we have this WebAssembly runtime in the web browser, and we can interact with, the WebAssembly runtime from the JavaScript runtime. And we can also interact with everything that you see in the web browser, which is the DOM, or document object model, behind it, right? So everything can talk to each other. And here's a very, very brief how-to. If you want to start such a project, I found this very nice blog article here on lennonbr.com. It's about Rust WASM packs, so that is like the tooling around that. Rust WASM is like the, overall project, and this here is the link to it if you want to have a look as well. Well, the TLDR is, you use cargo to install WASM pack, and with the WASM pack, you create your new project. So that will create a directory with the name of that project. It will ask you a few, like, some interactive questions where you can say, okay, I want this and this feature. It's very, very short, and you have created a project. It's a bit like a wizard that you would otherwise click through. It's just on the command line. Then we need some glue code. So in web development, there is a very nice tool that we use that is called Webpack. And what Webpack does is it creates such a convenience for us that we can eventually import the Rust code in our JavaScript code. So from a programmatic point of view, it feels just as if you were importing another JavaScript module. Very, very nice. So yeah, if you need some extras, I also highly recommend adding this here a Rust crate that is called Glue Utils. Glue as in GLOO, but yeah, it's a bit of a word game. You will see it if you look at their documentation. Well, the Rust side then is very easy. If you write some Rust code, that is what it looks like. So if you know the Rust language, this might be familiar. You have some use statements here. That is how you import other, well, libraries or crates, as we call them in Rust. We can use serialization from the 30 project. Like here, I'm defining a struct. I'm using this annotation here, so I can, serialize some data from the Rust side and transfer that over to the JavaScript side. And it's really as simple as this. Now for the WebAssembly part, we use this annotation called wasm bindgen. With that, our function that we have right below here is now exported so that I can also import it on my JavaScript side again. And that's already all the magic. There is literally not much to it. Now on the JavaScript side, as I said, I can now import something. In this case, I have a function that I call sum_fun. I import that from my Rust package. Let's say I created a project called RS with the wasm tool that I showed you earlier. And in that, there will be a subdirectory called pkg. It might be that you can also rename this. It's just the default thing. Well, you can import this function. Now you can call this function directly from your JavaScript context, and you get the result from it, and so on. And that is essentially also what we're doing in the device tree project. So in dtviz, if you look at the Rust code, it is literally just like, I don't know, maybe 30 lines of code, if at all. And the function itself only has 5 statements. Well, now the only issue is this here is now a synchronous call. So that would be blocking. That would be blocking your UI. But yeah, if you want to go beyond that, I also recommend looking at these articles here, which are on the usage of futures, or as we call that in JavaScript, it's like the counterpart, if you will. We have the promises, so that is for asynchronous processing, right? So you can also do, like, if you want to do large processing in the background, you can use that feature so that your user interface still remains responsive. I've used that in some other project, not yet in dtviz, but just so that you know. Well, and with that, thank you very, very much already. I think I just went a few minutes past the 20 minutes announced. Yeah, this here is the obligatory slide if you want to follow me on the social medias and so on. And also if you want to find the project, as I said, it's on GitHub under Platform System Interface, and I will share those slides later so that you can recap them.